design project sponsored by Nimbus Labs, and it is called Aerial and Water Collaborative Sensor Deployment and Recovery.
Okay, so my name is Joseph Obama. I'm a computer science major, and to talk a little bit about the company that sponsors this project. So we were sponsored by the NIMBUS Lab, and NIMBUS Lab is a company or a group that focuses on researching into solutions, making solutions using dependable UAVs. Basically, they make robots and drones, and they use all of these advanced technologies to solve real-life problems.
So our project had a few stakeholders. First, we had Eric Detweiler. He was our main sponsor, and he is co-director of Nimbus Lab. It was also sponsored by Brittany Duncan, the other co-director of Nimbus Lab. And in addition to us being someone who has a stake in its success, we had future Nimbus Lab grad students who may be working on this, the faculty and lab directors, and also the science partners at other institutions, because as we get into explaining what our project was and what our problem was, we are partnering with other institutions down the road.
Okay, so we were a team of 6 at the beginning of last semester, but one of our team members graduated, so we came down with a team of 5 for this semester. So we have Abby here, who is our team leader. She took over the lead from the previous leader. And we have Nick Coloran, who was our dev manager, and also Jeff Duranty, who was our lead developer, and myself and one other team member, Leo, who we were developers.
Yeah, and in addition to that, our tribe lead was Jeff Falkenberg. And so a little bit about our problem. Why did we need to create this aerial solution? So there are different terrains that scientists need to constantly monitor, and sometimes they're difficult to reach. They may be in cold Arctic climates, they may be hard to get to via vehicle. There are a lot of different factors, but we wanted to specifically focus on the topography of Alaska, because it has been changing due to beavers building their dams and rivers, and that's been causing the permafrost to melt quicker. And so we want some way to monitor and kind of look about what is happening without having to freeze in Alaska.
Okay, so with this, we got the opportunity to create a way to monitor the beaver ponds, and also so with the solution that we had, like building a boat, so we are able to deploy sensors that are able to monitor the conditions of these areas for several days, and then because it is a small boat, and then everything is done autonomously, we don't have to have like a lot of people working long hours trying to take readings from these ponds. And also we are able to get the opportunity to reduce the amount of disturbances we cause the environment, because instead of having a big boat on the pond, we have this small boat on there, and also reduce the amount of equipment used from a bigger boat to a small boat.
Yeah, so like Joe said, our solution built is a remote control boat which deploys and recovers sensors in these ponds in order to reduce some of that pollution and that work effort that goes into actually physically monitoring it with staff. It was inspired by the Ducky Pond project that was done at MIT, which created a bunch of autonomous boats that were a lot bigger than what we needed, but were able to drive and do similar functions that we wanted to do. We also had a weight requirement, and so that was probably the hardest part of this project, is drones can only carry a certain amount of weight, so our goal was to keep it around 4 kilograms so that we could deploy it via M600s. And we also wanted to create it so that future work done on it can be autonomous. And so we did not make it autonomous, but it definitely has the groundwork and the foundation that if someone else or another team would like to go and make it autonomous, it could be.
Okay, so this was the first build that we made. So you can see it doesn't look pretty, it doesn't look anything fancy, and then we basically had used pool noodles for the pontoons, and then we had this container on top of that. So we were trying to like test the concept to see if it was something that we can work with, and then also make sure that we can have something that floats and then move around a little bit, and then see if we can actually like have this concept into something that can be actualized. So, but a few cons that we had with this was that the container wasn't waterproof, and then we are dealing with water here and electricals, and these two don't work together. And we did not also have PID controller for straight light driving. So to have like boats, robotics and stuff like that, to be able to drive straight, or even for small cars and RCs, you have to have PID controllers to be able to drive straight. But we wanted to test the concept, so we didn't have all of that. We just wanted to get something moving. And also we did not have areas to mount the deployments. So we are basically going to deploy sensors in the ponds, but this didn't have any of that. So we didn't have the deployment system or the retrieval gear.
Yeah. You may be thinking, well, I thought that I was at a computing senior design showcase. Why am I learning about permafrost, and where's the computer on this? Well, that's what our next part is. We decided to control our system with a Raspberry Pi 4+B, which ran ROS, Robotic Operating System, which created a state machine that controlled an Arduino. It was hooked up to kind of as the peripheral for all of the sensors, the motors, the deployment, and the retrieval system. And this system of the ROS and the ROS on the Pi and the Arduino carried through each of our iterations of this boat. We also implemented an IMU for driving capabilities, and this is the thing that enables us to implement that PID controller and make sure that the boat is driving straight and corrects anytime it gets off path.
Okay, so after we had the first version of NIMBUS, so we went to the second version. So this is where we began to add sorted components, and now we had something that didn't look super sleek, but it was getting there. And also we added the state machine, and also we were able to add the retrieval mount, so the piece that you can see over there with the fork-looking thing. So that was the concept, the approach that we are going to go for to pick up the sensors when it was time for retrieval. But we didn't have the deployment system on here. And some issues that we had with this was weight distribution. So basically, the fork was giving so much weight at the back of the boat, and so it would tilt a little bit.
So that led us to our final NIMBOT iteration, and as I said, it was a ROS core ran on the Pi, and it sends serial messages to the Arduino, which then controls each of its states and allows it to do things like drive, retrieve the sensor, and deploy the sensor. We also we created our own waterproof box that Joe was actually really great at laser cutting and designing, because we wanted something that was cheap, because a big part of this was creating a modular and cheap solution that could be recreated at little cost. And so we added the deployment feature, which is that circle on the back that pushes sensors off the boat. The boat can deploy up to 4 sensors at a time. And we improved the retrieval arm with reinforcing it in a carbon fiber mount, and increased the efficiency of our ROS state machine. In addition to that, we created our own PCB board. This was a really fun part for me because it was my first time designing a PCB board, and it standardized the connections and allowed us to have mounts that were soldered and stuck, but could then be, we call them pop socket connections. So we use DF3 connectors so that if a motor would break when you're out in the field, you wouldn't have to go back and resolder it. You could just pop it off this PCB board, pop it back on, and it would have the stability of solder without the permanency of it. And it also helped simplify the assembly of it.
Okay, so with this, the team were able to get opportunity to work together with peers as a team, bring down ideas to create solutions for real life problems, and then we were able to continuously work and optimize something that was totally out of nowhere. And we also able to like practice giving ourselves like pace and also milestones to work and hone our skills and also like understand the impacts that we put on the environment through the solutions and the things that we do. So with this, we would like to thank you all for your time.